Welcome everyone. Welcome to today's class. And in today's class, as promised, we're going to be talking about what we call gas laws, of which in general, I can just write this guy, which will be our main focus, the gases. So one of the most important things that we know when it comes to gases, which are uh, one of the three states of matter, apart from the solids and liquids, we know to say atoms and gases are widely separated. The atoms that we find in gases are actually uh, widely separated, and due to this, the forces that are between these individual molecules of gases are actually very uh, low. The forces that act between each individual gaseous molecule are very low because the gaseous molecules are actually widely spaced. And if you have a gas here in a container, you're going to notice that since these guys are sparsely packed, they are able to move freely. It's one of the states of matter where we have substance moving freely. And if they are contained in a container, you're going to notice that these gaseous molecules are going to be um, actually impacting the container, or they are going to be hitting the container. They're going to be exerting a force on the surroundings per unit area. And that physical property is what we call pressure. So in this topic, we're going to study the four physical properties that are found in gases and how they affect the behavior of gases. Of which physical properties are we talking about? We are going to be talking about what we call pressure, which is force per unit area. We're going to be talking about volume. We're going to be talking about temperature, and also the number of moles. So we're going to look at these four properties and how they affect the behavior of gases in different scenarios using what we call gas laws. So there are basically, I can say we have four different gas laws that explain how these four physical properties that I've written here relate to each other when it comes to gases. And we are also going to actually learn how to apply these different laws or fundamental laws or basic laws on gases to see how these four characteristics, or rather physical properties that are have outlined there, are going to affect the behavior of these gaseous molecules. So let's go into the first law without wasting much time. The first law, or the first gas law that I'm going to talk about, is what we call the Boyle's law. The Boyle's law. And what does the Boyle's law actually talk about? Well, what is the concept between the 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 Boyle's law? So to represent the Boyle's law in a mathematical way, before I even talk about what this principle talks about, we're going to say pressure there by temperature is equal to what? Is equal to constant. I can say this is proportional to a constant K. And what does that, or what does this relationship actually represent? Or pressure here, pressure, temperature, or pressure volume rather, not pressure temperature, sorry. PV is equal to a constant K. Now, what is this Boyle's law, or this relationship, or this law, the first law that we are discussing, actually explaining the relationship between pressure and volume? So you're going to notice to say, if you have a container, let me say I have a container here. If the volume of this container is very small, or the volume of the container is small, it is going to reduce the distance between the individual gas molecules that we have in this container. And as such, what are you going to notice? Those gaseous molecules are going to be frequently coming into contact with the surfaces of the container, or with the surfaces of its surrounding, or they will be hitting the surrounding much more often, as opposed to if you had maybe a bigger sized container or something, of which that's the opposite case when you increase the the size or the volume of your container here. So I've put four gas molecules in both of these two containers, and you're going to notice that In this container B, the frequency at which the gases or the gas molecules are going to be impacting or to be hitting the surfaces of its surrounding is actually smaller than the frequency at which the gas molecules in container A are going to be hitting the surfaces of its container. And why is that happening? It's due to the relationship between pressure and volume that was explained by this guy known as Boyle's or Robert Boyle's, which we call the Boyle's law. So what does this law actually state? It states to say at constant temperature, at constant temperature and number of molecules. So you can see that's why I've drawn in both containers. I've put four gas molecules just to show the difference. We are maintaining the same number of molecules, also constant number of molecules, of which number of molecules are represented by N. I just put N for moles. So at constant temperature and constant number of molecules, the absolute pressure of this gas and its volume are inversely proportional. So that means the pressure of this gas is actually inversely proportional to the volume. And what does it mean? That means if you increase the pressure, the volume is going to decrease. If you increase the volume of this gas, the pressure is going to decrease. And we can explain it using these two diagrams that I've shown here. So this relationship between pressure and volume when constant temperature and constant number of molecules are maintained is that they are inversely related. Increasing the other is going to automatically lead into the reduction of the other one. Hence, I've put this equation here to represent the relationship between temperature, or rather pressure and volume when constant temperature and constant number of molecules have actually been maintained. So that is the first law, or the first gas law, that we're going to talk about using this equation that I've actually drawn here. Okay, so let's look at another equation that we call the Charles law, or the second law, which we're going to call the Charles law. The Charles law. So the Charles law is actually going to show us the relationship between volume and the temperature. The first one was showing us the relationship between pressure and volume. Now let's look at the relationship in gases when it comes to volume and temperature. So this law states to say when you have constant pressure, which means you've maintained constant pressure, the pressure has been maintained constant, and also the number of moles has been maintained constant. What are you going to notice? You're going to notice to say the volume of this gas, which means the volume of this gas is going to be proportional to the absolute temperature. So volume of the gas is going to be proportional to temperature. It's going to be directly proportional to the temperature of the gas, provided that you've maintained the constant pressure and the constant number of moles. So what does this mean? This means to say if you heat up a gas, if you increase the temperature or the amount of thermal energy in a gas, you're going to notice that even the volume of that gas is going to expand. So this equation that we've put here can also be simplified in such a way that the ratio between the volume and the temperature will actually be equal to what? Will actually be constant, like this. Why? It's because once one of these two guys is increased, when these two have been maintained constant, the other one is also going to increase at the same rate or with the same amount. So the ratio between volume and temperature, when number of moles and pressure have been maintained constant, is also constant, or they are directly proportional to each other, which means the change of the other is going to affect the other in such a way that it is going to have a similar amount of change and also in the same direction. And we talked about this even when we are talking about thermal energy. So when you heat up substances, they usually expand. We also looked at the volume of spill. The volume of spill, although in that case the pressure wasn't maintained, because at the end it leads into spilling. But what you should understand is that as you are heating up a gas is going to expand in its volume, and it is going to expand at the same rate as the temperature that you are supplying. Hence, you're going to see this equation to say V1 or V, volume over temperature, should be equal to a constant like that. Or if you have V1 and T1 here, increasing these two guys is going to lead us to the same amount in increase. So V1 over T1 should be equal to what? Should be equal to V2 over T2. And this is what we call the Charles law. As simple as that. We've explained what the Charles law is. And we go to the third law. Okay, so C, which is the third law. The third law actually talks about it's known as the Amonton's law or Gay-Lussac's law, which is a very common name. So I'll say this is Gay-Lussac's law. So what does the Gay-Lussac's law actually talk about? It just shows us the relationship between pressure and the temperature. Temperature and the pressure. Well, I wanted to write it in another way. So what's the principle behind the Gay-Lussac's law, or what's the concept behind the Gay-Lussac's law? So we're going to notice to say this law is stating us to say when you have a constant volume, and you also have constant number of molecules. Constant number of molecules. What are you going to notice? The pressure is proportional to the temperature increase, like this. Pressure is proportional to the increase in temperature, which means the pressure and the temperature are directly proportional to each other. Now, why is this the case? We've maintained the same volume, we've maintained the same number of molecules, but using the kinetic theory of gases, you're going to notice that whenever you apply thermal energy to a gas or you apply thermal energy to a substance, what does it do? It increases the heat in the system, or it increases the temperature of the system. And how does the temperature of a system actually affect the pressure of the system? It's because when you supply thermal energy or supply in heat, when you supply heat to a substance, it is going to lead to what? It is going to lead into increase in kinetic energy. Ke. So there will be increase in kinetic energy, and kinetic energy is the energy that is possessed on a substance due to its motion. So it is going to increase the motion of those substances such that they will start hitting the surrounding at a much faster rate. But we're having the same volume, we're having the same number of molecules. It's just that the molecules have actually gained more and more kinetic energy, and as they are gaining more kinetic energy, what is happening? Their motion, their momentum is increasing. And as their momentum is increasing, they are going to start um, striking their surrounding, striking the surfaces of a container at a higher rate, as opposed to when you have lower temperature or when the gas is having a lower temperature. So since this is uh, directly proportional like this, what are we going to notice also is that the ratio of these guys is actually constant, which means pressure over temperature using the Gay-Lussac's law should be equal to what? Should be equal to constant, which can also be written as what? The pressure 1 over temperature 1 should be directly proportional to when you increase pressure to a certain amount, known as pressure 2, over temperature 2. So this is what Gay-Lussac's law is talking about when and only when the volume of the gas is maintained and also the number of molecules is also maintained. This is mostly experienced when if you've ever used a pressure cooker. A pressure cooker actually follows this principle very well because you have the same amount of molecules inside the pot or inside the cooker, but as you start increasing the temperature of um, of the surrounding or of the system, you actually notice what is happening. The pressure will increase such that even the valve will open and etc. and etc. So that is what the Gay-Lussac's law actually talk about. So we've talked about the three laws of or the three gas laws, where we've talked about the Gay-Lussac's relating pressure and temperature. We've talked about the Charles law, which is relating volume and temperature, and we've also talked about the Boyle's law, which is relating pressure and volume. Now, what can we do? We have to know that we can combine these three laws that we've just talked about, and we're going to come up with one law from these. So we can say combined gas law. So how are we going to come up with a combined gas law? So we've examined the relationships of all those guys that we've under each distinct law that we've talked about, and we can combine those guys into one simple equation, such that we're going to see to say the pressure one, volume one over temperature one should be directly equal to the pressure two, volume two, and the temperature two, like this, which means the ratio between these two guys is what? Is constant. Or pressure or initial pressure multiplied by initial volume over initial temperature should be directly proportional to final pressure multiplied by final volume over final temperature. So that is what we call the combined gas law. And how is this combined gas law actually coming about? Or if you are interested in knowing. So this is actually very simple, very, very simple, because we explained each of these laws to say we have this relationship when it comes to the Gay-Lussac law. And if we combine this relationship that is with the Charles law, you're going to come up with what kind of an equation? Let me check. It's pressure, volume, temperature, volume. Okay, so that means we're having volume as a numerator like that. And here, what are we having? We're having pressure as the numerator. Whilst on both sides, we're having temperature as the denominator, of which the case is the same when it comes to the Boyle's law. This one. Everything is one and the same. So that is how we can come about the combined gas law. So this guy. So from this combined gas equation or gas equation, what can we notice? We can also notice to say the two sides of the equation should be directly proportional, which means I can also write this as what? As P1 V1 over T1. This should be equal to what? It should be equal to constant. It is a constant. And this is how we're going to lead into what we call the ideal gas equation. Or before we come to the ideal gas equation, we can also talk about what we call the Avogadro's law. The Avogadro's law. So this is the third gas law or the fourth gas law that we're going to talk about today. And what is the concept between the Avogadro's law is that uh, the volume of the gas is directly proportional. So which means the volume of the gas is directly proportional to the number of moles of the gas when temperature and pressure are held constant. So which means volume is directly proportional to the number of molecules, the number of moles of that gas when temperature is constant, but also pressure is constant. Like this. So how can we come up with an equation of this guy? Since the volume is directly proportional to the number of moles of this gas, that means the ratio of change between these two guys is equal to a constant. There's no change in a ratio. That means volume over number of moles should be equal to what? Should be equal to a constant K. Or volume 1 over number of moles 1 should be equal to volume 2 over number of moles 2 of this gas, or vice versa. We can put you can interchange this since the ratio isn't changing anyway. We can also say N over V is equal to what? Is equal to K. Okay, so that is the relationship between the volume of a gas and the number of molecules as explained by the Avogadro's law. So now from this combined equation that we found here, this one, this guy, if we integrate this last law, which is the Avogadro's law, this one here, what are we going to come up with? So this is very simple. You can see to say here, let me just put that one here. I had P1 V1 over T1 being equal to P2 V2 over T2. Then we have the Avogadro's law, which I'm trying to integrate into this formula, which is telling us to say when you have constant pressure and constant temperature, V1 over N1 should be equal to what? Should be equal to V2 over N2. So how are we going to integrate this formula into these two guys? We already have volume here. The only thing missing into this formula, the combined formula, is the number of moles. So we're going to integrate it the way it is as a denominator here. I don't want to go into details of deriving this equation, otherwise we might waste time. This is just something that you can memorize. Just follow the way it is and understand using the concepts that we've explained. So we're going to say pressure 1, volume 1 over temperature 1. I'm going to integrate this. Number of moles 1 should be equal to pressure 2, volume 2 over temperature 2 multiplied by number of moles 2. Like this. So this is now the combined or the fully combined gas equation that we can come up with by putting all the four laws that we've discussed together like this. And since you can see to say they are directly proportional to each other, which means the change in pressure and volume is directly proportional to the change in temperature and number of moles. You can actually also come up with this equation as P1 V1 over T1 N1. This is actually equal to a constant K. Now, what is this constant K that we are seeing here? What do we call this constant? If you have any idea. Okay, so we call this constant the ideal gas constant. So K is equal to the ideal gas constant. Like this, and it is represented by the letter R. So which means if I want to replace where I have K in this equation with R, I can just say pressure 1, volume 1 over, or not just that, since I'm now dealing with a constant, I can remove the initials there, over T, N like this. This is equal to what? This is equal to the ideal gas constant, R like that. Now, R has different units. It actually has different units based on the units, and it will be given based on the units that you are using for pressure, for volume, and for temperature also. So R is also going to depend, and the only thing you should do is use the appropriate units of R. Even the values differ depending on the units, but use the appropriate units of R according to the pressure, volume, and the temperature that you have been given. Those units should be related to R, because the values of R are also going to differ depending on the units that you are using for those guys that I've just talked about. And from here now, this equation is what we call the ideal gas equation. The ideal gas equation. And mostly, if you notice, you won't find this equation in this form. How? It's because I'm just going to put an over one there, and I'm going to cross multiply this equation. So mostly I'm going to find the ideal gas equation in this form, to say pressure multiplied by volume is equal to N R T. Like this. I'm just multiplying this by R there and coming up with this equation, of which this equation is what we call the ideal gas equation. Okay, so that was those are the four gas laws that I wanted us to talk about. We'll see how those four physical properties that we discussed initially actually affect the behavior of gases using these four laws that we just talked about, and also actually look at the mathematical equation that relates the four physical properties that we've talked about also, and also coming up with what we call the ideal gas equation using all these four laws, and also the kinetic theory of gases. So when I reach that part, that means I'm done with it, whatever I wanted to talk about today. And next time we meet, we're going to solve tutorial sheet 2.